Greetings and welcome back. I'm going to go and talk briefly about part 5 of the slides. Let me share my screen. I think you are quite familiar with this topic, K nearest neighborhood. We have spoken of this in the past. We talked about Euclidean distance in previous recording. This is going to serve as a refreshing slide, I would say. So what is happening is that you could potentially decide about how close your unknown sample is going to be to the center of the clusters that you have. And depending on that distance, you're going to classify this either belonging to the green dots, green circles, or the basically orange kind of a star points. So that's what we did in the past. And the way we did it, we actually used a function called a Euclidean distance. It was called distance function. Distance function is very simple to do. You take the subtractions of the coordinates, and then you take it to the power of 2, and you have the square root of that. That's going to be the distance function. And you also, if you remember, we had something called epsilon. That epsilon was the distance metric. We would say, okay, the distance threshold. We are going to say if your distance is less than the threshold for that specific center of cluster or gravity point of the cluster, then this one is going to belong to that cluster. That's what we did quite a while back. One of the things, one of the additional note that I would like to ask you to pay attention to is that often we do normalize. The reason we want to normalize because some of the points are going to be far off and some of the points are going to be too small. And by normalization, we are going to basically scale them down. Not that the relation is going to vanish. The relation doesn't vanish, but it's going to be a scale down. So there are many ways of normalizing, and one of the simplest ways of normalizing is min-max normalization. We spoke of min-max normalization in the past. If you tell me what is the maximum of the sample, what is the minimum of the sample, I'm going to take the new sample, and then V minus the minimum A divided by max minus min, and then that's going to be the mapped sample. So that's how we are going to map the value. Basically, one of the things that I would like to state and close this chapter, as we have extensively talked about it in the past, is that if it is, if the attributes are basically nominal and they are not numeric, what do we do? We spoke in the previous recording that you could do a mapping between nominal and numeric. You could potentially assign 1 to red, and 2 to green, and so on. At the same time, you could potentially study the distance in this way. This is really nice way, easy way. You don't want to basically assign binary values necessarily to the actual attribute value. If the two attributes are identical, for example, both of them are young and young, obviously the distance is going to be 0. If the twos are different, you could potentially say 1. This is a simple way of identifying the distance between nominal values. But again, if you have more than 2, then it will not be easy to say 0 and 1. If you do that, you're actually putting many of these nominal in one cluster as yes or 1. And many others would be in 0 cluster, and that's not going to be helpful. You're going to reduce the clarity, you're going to reduce the basically accuracy by lumping them together, all of them in one cluster, and calling them 1 and calling them 0. So this is correct, this approach is correct if you have only 2 nominal values. But if you have more than 2, then you have to come up with a creative way of doing that, and then to be able to basically interpret the end result. That was part 5, and next we will go to part 6.